In this module, you will learn about the function, layout, and the operating principle of hydraulic motors. The following learning objectives should be achieved in this module. You should be able to explain energy conversion as the primary functions of hydraulic motors. You should be able to describe displacement and direction of rotation as central distinguishing features of hydraulic rotation motors. You should be able to list 6 standard types of hydraulic motors and their most important features. You should be able to describe the layout and operating principle of multi-stroke radial piston motors. You should be able to understand sample calculations of output speed and output torque. You should be able to name the causes of losses during energy conversion and describe the typical efficiency of hydraulic rotation motors. This module gives you several opportunities to check your own learning progress. These intermediate tests are not saved, nor do they count toward your grade. You can repeat or skip the intermediate tests. At the end of the module, there is a final test which you have to pass in order to move on to the next learning module. In a hydraulic system, hydraulic motors are energy converters. They draw in hydraulic fluid and convert hydraulic energy into mechanical energy. Unlike hydraulic cylinders that move in and out in a straight line, hydraulic motors rotate. Hydraulic rotation motors cause an output shaft in the motor to revolve continuously. This drives road rollers or drilling heads of tunnel boring machines, for example. In hydraulic systems, hydraulic pumps convert mechanical energy into hydraulic energy. Then hydraulic motors convert the hydraulic energy back into mechanical energy. You can see the principle at work here in a hydrostatic travel drive for a wheeled loader. A hydraulic pump converts the drive power supplied by the engine into hydraulic energy. This energy is stored in the hydraulic fluid, which is fed to the hydraulic motors via lines. The motors convert pressure and flow in the hydraulic fluid back into drive power for the loader wheels. Return lines carry the hydraulic fluid back to the hydraulic pump. Energy is converted both in the pumps and in the motors according to the displacement principle. This is why they are similar in design, although the operating principle is inverted for hydraulic motors. The principle of energy conversion is described in more detail using a gear motor as an example. It applies to all hydraulic motors regardless of the design of the displacement elements. Gears, pistons, or vanes are used in hydraulic rotation motors as displacement elements. Displacement chambers in the motor are pressurized with hydraulic fluid from the line connection on the pressure side. Pressure and flow act on the displacement elements, that is, on the gears. This generates torque that causes the output shaft to rotate evenly once it has overcome the resistance of the shaft. While energy is being converted, the hydraulic fluid moves from the high-pressure side to the low-pressure side and is discharged through the line connection. Pressure and flow determine output torque and output speed of a rotation motor. The circuit symbol shows the features of a hydraulic motor depending on its function within the hydraulic system. The symbol for an energy converter is a circle. The triangle pointing inward indicates the direction of flow and the type of medium, here a fluid. The rotation motor contains an output shaft and the curved arrow indicates its direction of rotation. In this example, the motor rotates clockwise when looking down on the output shaft. A hydraulic motor needs working lines to circulate hydraulic fluid. The diagonal arrow indicates that the inlet flow is variable. If the motor has a separate leakage line, the corresponding port is marked with a T or L. The symbol does not indicate the motor type. The process of energy conversion has to meet certain requirements that depend on the application. Rotation motors have to begin rotating from a standstill at maximum output torque and minimal startup pressure. Good startup behavior in a motor requires low moment of inertia, low friction, and low leakage losses. Rotation can be accelerated gradually and evenly, and the predefined speeds can be maintained precisely. Even with highly variable power demands from work elements, Hydraulic motors can adjust speed and torque almost instantaneously. Hydraulic motors allow the direction of rotation of the output shaft to be changed quickly and easily. Rotation motors have high power density and compact installation space. Small components compared to electric motors produce high output power. Hydraulic motors have a long service life. The lubricating and cooling effect of the hydraulic fluid contributes significantly to the components moving inside the housing with virtually no wear. The key parameters for hydraulic motors are their output torque and their output speed. Torque is produced by the pressure difference between incoming and outgoing hydraulic fluid and displacement. Speed is also determined by displacement and, moreover, by incoming flow. Displacement is the amount of hydraulic fluid that is passed through the motor during one revolution of the output shaft. Displacement is also comparable to the displacement of hydraulic pumps. If displacement is variable, output torque and output speed can be adjusted at the motor to suit the needs of the working elements. This is why there are hydraulic motors with fixed displacement and motors with variable displacement. Examples of these are the two axial piston motors, one fixed and the other variable. Variable motors can adjust displacement infinitely between a minimum and a maximum value, depending on their design. The suitability of a hydraulic motor for a working element depends not just on the type of displacement, but also on the direction of rotation of the output shaft. The output shafts of hydraulic rotation motors can rotate continuously in one or either direction. The axial piston motor in bent axis design shown here is suitable for reversing operation. The motor rotates clockwise or counterclockwise depending on the working port through which hydraulic fluid is supplied. Motors in reversing operation generally return leakage through a separate port. The inlet and outlet of hydraulic motors that can only rotate in one direction are established accordingly. These motors usually take in leakage internally. Alternative working and drain ports are often added to the housing of a hydraulic motor for easy installation. The direction of rotation has to be clearly indicated both when planning a hydraulic system and installing a hydraulic motor. For consistency, the direction of rotation is always viewed from straight down on the end of the output shaft. The triangle in the circuit symbol indicates the flow direction. If the hydraulic fluid is supplied through port A, the output shaft in our example rotates clockwise. If the shaft should rotate counterclockwise, the hydraulic fluid has to be supplied through port B. This is only possible if the motor is designed to be reversible. The two triangles in this circuit symbol indicate that the hydraulic motor is designed for two flow directions and is reversible. Depending on the supply direction, the output shaft in this hydraulic motor rotates clockwise or counterclockwise.
Very good. All your responses are correct.
In practice, gears and stroke pistons are proven displacement elements in hydraulic motors. The main representatives of these design principles are included in this overview, classified according to fixed or variable displacement. Gear motors always operate with fixed displacement. Variable displacement requires that a displacement element can increase or decrease the space for hydraulic fluid. This is the case with hydraulic motors that operate according to the stroking piston principle. Piston motors also differ in their piston arrangement. Whereas the displacement elements in axial piston motors are arranged in a circle parallel to one another, they are arranged in a star shape around an output shaft in radial piston motors. Axial piston motors come in various designs, including bent axis and swash plate. The pistons are at an angle to the output shaft. This type of motor comes with fixed and variable displacement. Multi-stroke radial piston motors come with fixed displacement or as a switching motor. The switching motor can be operated at full or half displacement. Variable motors come in bent axis and swash plate design. Bent axis variable motors come with 7 or 9 pistons. The 7-piston model is the standard version and is designed for a nominal pressure of up to 400 bar, 5,800 psi. The 9-piston model has a nominal pressure of up to 450 bar, 6,500 psi. The 9-piston model also has better low-speed behavior and higher efficiency, making it especially suitable for winch drives and energy-efficient travel drives. Swash plate variable motors only come as switch motors. That is, the motor can either work at the maximum swivel angle for high output torque and low speed, or at the minimum swivel angle for high output speed and low output torque. Swash plate variable motors operate at a nominal pressure of up to 280 bar, 4,000 psi, or in the medium pressure range. Gear motor power depends directly on flow and pressure difference in the motor, since the displacement cannot be varied. The design determines the volume of the displacement chambers, and this space between the gear teeth cannot be changed. Gear motors are compact and lightweight. They are among the high-speed engines and give off both a large starting torque and a high continuous power. For motors which are intended for only one direction of rotation, high and low pressure side are determined. They can no longer be reversed. Motors can, however, be configured to be reversible. The resulting leakage is usually drained through a separate drain port. Gear motors are often used in construction machinery, agricultural technology, and in buses and trucks, and are especially suited for driving conveyor belts and hydrostatic fan drives. There are basically 2 types of axial piston motors. In the bent axis version, the pistons are arranged in a rotating cylinder at an angle to the output shaft. In a swash plate motor, the pistons are parallel to the output shaft and transmit forces through a suitable sliding disc. Both designs can have fixed and variable displacement. Variable motors that can infinitely vary their displacement between a minimum and maximum value regulate output torque and output speed well. The light weight of swash plate motors also allow for very short stroking times. Axial piston units have good stability and good internal sealing. They can be charged with high pressure. Axial piston motors output very high speeds, classifying them as high-speed motors. Their compact installation space helps to keep drives small. They are used in winch drums and drive milling drums. Axial piston motors are also used as the travel drive for crawler and wheeled vehicles, and can be found in the slewing drives of excavators and cranes. Unfortunately, that is not correct. Rexroth MCR motors are radial piston motors with external support that are available as fixed displacement motors or as switching motors. The switching motor can operate at full or half displacement. These motors typically have high torque in conjunction with low speed, making them low-speed motors and smooth startup. They are compact, have high power density, and are not sensitive to impact loads. Due to their robustness and high torque, radial piston motors with external support are used in many sectors of mobile hydraulics. These hydraulic motors can be used directly in the wheel hub as a travel drive, as seen in road construction machines, forklifts, elevating work platforms, skid steer loaders, as drum drives for concrete mixers, and in industrial hydraulics. The circuit symbol for an MCR motor is the symbol for a hydraulic motor with fixed displacement, reversible direction of rotation, and drain line. MCR radial piston motors come with displacements between 160 to 3,000 cubic centimeters per revolution. They operate at a maximum speed of 115 to 875 revolutions per minute and a nominal pressure of up to 400 bar, 5,800 psi. MCR radial piston motors can output a maximum torque of up to 19,100 Newton meters, depending on size. MCR radial piston motors come in different models that differ primarily in the mounting flange or housing. These allow a wide variety of radial piston motors to be produced easily, which can then be used for special applications. The MCRF motor is the most common model and is primarily used in forklifts, road rollers, compact pavers, and elevating work platforms. MCRA motors for driving slatted frames in pavers. MCRW motor for higher wheel loads. MCRH motor, also called a hydrobase, for concrete mixers. MCTT motor for compact track loaders and trench rollers. MCRX motors are installed in the slewing drive of mini excavators and midi excavators. MCRX motors are installed in the slewing drive of mini excavators and midi excavators. MCRD and MCRE motors, primarily for industrial applications, such as rubber, plastic, and paper production systems, or in recycling systems. The MCR is a hydraulic motor with a radial set of pistons as a rotary group. It is a low-speed motor with high torque that operates on the multi-stroke principle and outputs torque directly onto the drive shaft 1. MCR motors can be used in open and closed circuits. The radial piston motor consists of a front 2 and rear housing 3, as well as a rotary group with pistons 4, cylinder block 5, cam ring 6, also called a cam disc, rollers 7, and distributor 8. The cylinder chambers E are connected to ports A and B through axial bores and the annular channels D in the distributor. The front half of the housing usually has 2 tapered roller bearings 9 that are able to absorb high axial and radial forces. A shaft seal 10 is designed to seal the unit and prevent leaks. The duocone seal 11 protects the front tapered roller bearings from dust and dirt. Adding a holding brake 12, called a multi-disc brake, provides safety for many mobile operations and ensures that the motor cannot run when the equipment is not being used. The radial arranged pistons are pressurized in the cylinder bores and use the rollers to press against the cam ring. The counterforce on the cam ring generates torque that is transmitted to the drive shaft in the cylinder block through the splines. Once the torque exceeds the shaft load, the cylinder block rotates and causes the piston to move, working stroke. At the end of the stroke, the piston returns to its bore, return stroke, and the fluid flows to the motor's outlet channel in the rear housing. Output torque is generated by the force caused by the pressure and the piston area. It grows with the pressure difference between the high-pressure side and the low-pressure side. Output speed depends on displacement and is proportional to the incoming flow. The number of working and return strokes corresponds to the number of times the cam ring is lifted multiplied by the number of pistons. In switching motors, 2W, the motor can be switched to a mode of lower output torque and high speed, in that only half of the piston is pressurized with hydraulic fluid. In this soft shift mode with reduced displacement, speed increases while flow remains constant. Radial piston motors with external support are compact and robust, and have high volumetric and mechanical efficiency. The mounting flange on the rear housing allows the motor to be installed directly on the vehicle chassis. The wheels can be mounted directly to the wheel flange with wheel bolts. Uniform concentric running, even at very low speeds, low operating noise, and absorption of high radial forces on the drive shaft are other benefits of the MCR motor. It is reversible, that is, it can rotate clockwise and counterclockwise, and freewheeling switching is possible. Sealed taper roller bearings keep out dirt and dust and ensure maximum reliability. Bent-axis axial piston motors come as fixed and variable motors. A typical example of a fixed motor is the Rexroth A2FM or A2FE hydraulic motor. It is used in open-circuit and closed-circuit hydrostatic drives and in mobile and stationary applications. In mobile hydraulics, it is primarily used in construction machinery such as mini and midi excavators, skid steer loaders, and wheeled loaders. In road construction, it is used in pavers, tandem vibration rollers, and single-drum compactors. It is also used in the slewing gear or winch drives of mobile cranes. Other application areas include drilling equipment, agricultural machines, forestry equipment, and various municipal vehicles. The circuit symbol for this kind of motor is the symbol for a reversible fixed motor with a drain port. The A2FM as well as A2FE fixed motor comes in 22 sizes, from 5 to 1,000 cubic centimeters per revolution. While the smaller sizes up to around 200 cubic centimeters are primarily used in mobile hydraulics, the larger sizes from 250 to 1,000 cubic centimeters are used in industrial hydraulics. Depending on size, the motor has a maximum speed range of 1,600 to 10,000 revolutions per minute at a nominal pressure of 315 to 400 bar, with temporary high pressure between 350 and 450 bar. The bearing kit, which absorbs forces acting in the axial and radial direction, is assembled on the drive shaft 1. A shaft seal 2, clamp collar and snap ring installed in the housing are used to seal the motor. The one-piece tapered pistons 3 catch the cylinder without the need for a drive shaft. Due to the spherical surface of the control plate 5, torque-free support of the cylinder 4 is provided. Due to the bent-axis design, torque is produced directly on the drive shaft. The pistons exert minimal lateral force on the cylinder, which reduces wear, increases efficiency, and improves starting torque. The port plate holds the rotary group in the housing and passes hydraulic fluid through 2 channels. The hydraulic motor can also be equipped with a speed sensor as an option. The cylinder bores are supplied with hydraulic fluid through the port plate and control plate. The pistons in the cylinder bores extend, which is converted into rotation at the drive shaft flange. The pistons also catch the cylinder and generate output torque at the drive shaft. Output torque grows with the pressure difference between the high pressure and low pressure sides. The output speed is proportional to the inward flow and inversely proportional to the displacement of the hydraulic motor. The direction of output rotation depends on the supply of hydraulic fluid. If it is supplied from the A side, left, the motor rotates clockwise. If it is supplied from the B side, right, the motor rotates counterclockwise. The Rexroth A2FM and A2FE fixed motor with axial tapered piston rotary group is used in open-circuit and closed-circuit hydrostatic drives for mobile and stationary applications. The gradual sizing offers extensive adaptation to each drive application. The large angle unit with a 40-degree swivel angle has high power density and small dimensions. The one-piece tapered pistons with piston rings produce good starting efficiency and high overall efficiency. The Rexroth A4FM motor is a swash plate axial piston fixed motor. It is used in open-circuit and closed-circuit hydrostatic drives for mobile and stationary applications, especially in tight spaces. It is primarily used in road construction machines, deep vibrators, mining, and offshore. The circuit symbol for this kind of motor is the symbol for a reversible fixed motor with a drain port and flushing port. The Rexroth A4FM Series 3 fixed motor comes in 8 different sizes, from 22 to 500 cubic centimeters per revolution. Depending on size, the motor has a maximum speed range of 1,800 to 4,250 revolutions per minute at a nominal pressure of 400 bar, with temporary maximum pressure up to 450 bar. The drive shaft 1 and bearings absorb axial and radial forces. A shaft seal 2, held in the one-piece housing 3 by a snap ring, seals the motor. The piston slipper pads 5 are hydrostatically mounted, slide bearing, to the sliding disc 4 by the retainer plate 8 and retainer ball 9. The angle of the sliding disc is determined by the housing 3, and thereby the pistons 5 perform a stroke movement while turning. Pressure on the piston causes it to pass down through the angled disc, sliding disc, and catch the cylinder 6. The cylinder rotates with the drive shaft, producing output torque. The forces at work in the hydraulic section of the rotary group, that is, the cylinder with pistons and control plate 7, are in equilibrium. The principle of the spherical control surface, its lubrication, the pre-charge pressure of the cylinder with springs, etc., is comparable to the function of the bent axis rotary group. The port plate 10 contains the pressure ports A and B. Depending on the flow direction, the motor rotates clockwise or counterclockwise. The cylinder bores are supplied with hydraulic fluid through the port plate and control plate. The pistons in the cylinder bores perform a stroke. Pressure on the piston causes it to pass down through the angled disc and catch the cylinder. The cylinder rotates with the drive shaft, producing output torque. Output torque increases proportionally with the pressure difference between the high pressure and low pressure sides. The output speed is proportional to the inward flow and inversely proportional to the displacement of the hydraulic motor. If hydraulic fluid is supplied from the A side, left, the motor rotates clockwise. If it is supplied from the B side, right, the motor rotates counterclockwise. The Rexroth axial piston fixed motor A4FM in swash plate design is specially designed for open circuit and closed circuit hydrostatic drives with minimal space. The fixed swivel angle makes the output speed proportional to the inlet flow and inversely proportional to displacement. Output speed can only be increased by increasing displacement. Output torque increases proportionally with the pressure difference between the high pressure and low pressure sides. The hydrostatically mounted slipper pads also ensure long expected service life and optimal efficiency. The Rexroth A6VM and A6VE Series 63 and 71 variable motors are examples of bent-axis axial piston motors. Series 63 operates at a nominal pressure of up to 400 bar and is equipped with a 7-piston rotary group. Series 71 operates at a nominal pressure of up to 450 bar and is equipped with a 9-piston rotary group. Axial piston variable motors with 9-piston rotary group run very well at low speeds and have good uniformity. Both are used in open circuit and closed circuit hydrostatic drives and are seen primarily in travel drives. Typical applications are standard excavators, mining excavators, wheeled loaders, telehandlers, mobile cranes, drilling equipment, crawlers, forestry equipment, and field choppers. The circuit symbol for this kind of motor is the symbol for a reversible variable motor with a drain port and flushing port, U. The Rexroth A6VM and A6VE Series 63 variable motor comes in 11 different sizes, from 28 to 1,000 cubic centimeters per revolution. The A6VM Series 71 variable motor comes in 6 different sizes, from 60 to 250 cubic centimeters. Depending on size, the motors have a maximum speed range of 1,600 to 5,555 revolutions per minute at a nominal pressure of 400 or 450 bar, with temporary maximum pressure between 450 and 500 bar. The bearing kit, which absorbs forces acting in the axial and radial direction, is assembled on the drive shaft. 1. A shaft seal 2, support ring and snap ring installed in the one-piece housing are used to seal the motor. The one-piece tapered pistons 3 catch the cylinder without the need for a drive shaft. The spherical surface of the lens plate 4 supports the cylinder 5 without transferring torque. Due to the bent axis design, torque is produced directly on the drive shaft. The pistons exert minimal lateral force on the cylinder, which reduces wear, increases efficiency, and improves starting torque. The maximum swivel angle and thereby the maximum output torque can be limited with a Qmax stop screw. 6. The minimum swivel angle and thereby the maximum output speed can be set by the Qmin stop screw. 7. The swivel angle is changed hydraulically using the stroking piston 8 and positioning trunnion 9. Here the cylinder including piston and lens plate is swiveled. The lens plate is smoothly mounted in a slipway. The swivel angle of the bent axis rotary group can be infinitely varied by using HD, EP, HA, and DA control. Two-point control, HZ, EZ, makes the swivel angle switchable from maximum to minimum. The cylinder bores are supplied with hydraulic fluid through the port plate and lens plate. The pistons in the cylinder bores perform a stroke, which is converted into rotation at the drive shaft. The pistons also catch the cylinder and generate output torque at the drive shaft. Output torque increases with the pressure difference between the high pressure and low pressure sides. The output speed is proportional to the inward flow and inversely proportional to the displacement of the hydraulic motor. Displacement is infinitely variable from Vg max to Vg min. The more the rotary group is swiveled back, the higher the output speed and the lower the output torque. The rotary group can be swiveled back to zero stroke. The direction of output rotation depends on the supply of hydraulic fluid. If it is supplied from the A side, left, the motor rotates clockwise. If it is supplied from the B side, right, the motor rotates counterclockwise. The Rexroth A6VM and A6VE variable motors with axial tapered piston rotary group in bent axis design is used in open circuit and closed circuit hydrostatic drives for mobile and stationary applications. The large control range of the variable motor meets high speed and high torque requirements, which together with a wide range of control devices results in cost savings due to the elimination of shift gearboxes and the option of using smaller pumps. The compact, robust motor has a long service life and high power density, as well as a good starting efficiency. Compared to fixed motors, variable motors have a wide control range for hydrostatic transmissions. The Rexroth A10VM and A10VE are swash-plate axial piston variable motors. They are used in open circuit, closed circuit, medium pressure hydrostatic drives, primarily in tight spaces. They are utilized as switch motors mainly in backhoe loaders, farm loaders, agricultural machinery, mini dumpers, and vibration rollers. The circuit symbol for this kind of motor is the symbol for a reversible variable motor with a drain port. The Rexroth A10VM and A10VE Series 52 variable motors come in 4 different sizes, from 28 to 85 cubic centimeters per revolution. Depending on size, the motor has a maximum speed range of 3,560 to 5,400 revolutions per minute at a nominal pressure of 280 bar, with temporary overdrive up to 350 bar. The drive shaft 1 and tapered roller bearings absorb axial and radial forces. A shaft seal 2, held in the one-piece housing 3 by a snap ring, seals the motor. The piston slipper pads 10 are hydrostatically mounted to the cradle 4 by the retainer plate 6 and retainer ball 5. The cradle is mounted eccentrically in the housing by slide bearings 3, so the variable motor is always at the maximum swivel angle. With the stroking piston and piston rod 7, the motor can be swiveled back to the minimum swivel angle. Q-min stop screw 9 can be used to set the maximum speed of the motor. The port plate 8 houses pressure ports A and B. When flow moves from B to A, the motor rotates clockwise. When flow moves from A to B, the motor rotates counterclockwise. The cylinder bores are supplied with hydraulic fluid through the port plate and control as well as distributor plate. The pistons in the cylinder bores extend. Pressure on the piston causes it to press down onto the cradle and catch the cylinder. The cylinder rotates with the drive shaft, producing output torque. Output torque increases with the pressure difference between the high pressure and low pressure side. The output speed is proportional to the inward flow and inversely proportional to the displacement of the hydraulic motor. If hydraulic fluid is supplied from the A side left, the motor rotates clockwise. If it is supplied from the B side right, the motor rotates counterclockwise. If the rotary group is switched from Qmax to Qmin, output speed increases and output torque decreases accordingly. The Rexroth axial piston switching motor A10VM in swash plate design is specially designed for medium-pressure hydrostatic drives in open circuit and closed circuit with minimal space. Output torque increases proportionally with the pressure difference between the high-pressure and low-pressure sides and increasing displacement. The stable bearing ensures long service life and very reliable output speed. Other features include a good power-to-weight ratio and low noise. The minimum swivel angle and thereby the maximum output speed can be adjusted from the outside. Two-point control can be directly actuated by an external control pressure supply, hydraulically or electrically by a solenoid switch. When designing a hydraulic motor for an application, both the output torque M and the output speed N have to be calculated. The torque that a hydraulic motor can output is the product of pressure difference delta P and geometric displacement Vg. The pressure difference is the result of the difference in pressure between motor input and motor output. Displacement is the amount of hydraulic fluid that is drawn in by the displacement chambers per output shaft revolution. The speed of the hydraulic motor is also determined by displacement and, moreover, by the incoming flow, QV. These formulas express the basic relationship when converting pressure and flow into output torque and output speed. The following can be derived from this. The higher the pressure difference and displacement, the higher the output torque. The higher the incoming flow and smaller the displacement, the higher the output speed. The following units are for the variables in these formulas. Output torque is in Newton meters, output speed in revolutions per minute. Pressure difference is in bar. Geometric displacement is in cubic centimeters per revolution, and flow is in liters per minute. The units do not have to be converted, and special technical data can be included by using a conversion factor in the formulas. This gives us practical numerical equations in which the output torque is multiplied by 0.0159 and the output speed by 1000. The advantage of numerical equations is that only numbers have to be used for the variables and no conversion is necessary. Note with these equations that efficiency is not yet considered. Using a simple example, the output speed of the gear motor in the diagram of the hydraulic system is calculated. The hydraulic fluid pressurizing the hydraulic motor has a flow of 29 liters per minute. The displacement of the motor is 40 cubic centimeters per revolution. We want to find the output speed of the hydraulic motor in revolutions per minute. Since we are using the numerical equation, the numbers 29 and 40 are used and we find the result. The theoretical output speed is 725 revolutions per minute. Note that the actual output speed will be lower since the volumetric efficiency of the motor has not been considered. After the output speed of the gear motor is calculated, the output torque should be determined. The pressure difference between the working ports is 250 bar. The displacement is 40 cubic centimeters per revolution. We want to find the output torque M in Newton meters. We put the numbers in the numerical equation and get the result. The theoretical output torque is 159 Newton meters. The actual output torque will be lower since the mechanical hydraulic efficiency of the motor has not yet been included.
Very good. All your responses are correct.
Every kind of energy conversion includes losses, even the conversion of flow and pressure into output torque and output speed. The balance between supplied power and output power is described in hydraulic motors by volumetric efficiency and mechanical hydraulic efficiency. Volumetric efficiency is based on losses of usable hydraulic fluid. A part of the flow supplied by the hydraulic pump is also lost in the hydraulic motor due to leakage. For example, hydraulic fluid can leak out of gaps between pistons, cylinder, and the spherical surface. Volumetric losses reduce speed. Mechanical hydraulic efficiency refers to losses due to friction. Mechanical friction occurs between contacting parts, such as on the bearing of the output shaft. Fluid friction occurs when, for example, hydraulic fluid flows through the channels. Mechanical hydraulic efficiencies reduce the usable pressure difference in the hydraulic motor, thereby reducing output torque. Pressure and speed conditions in the motor affect both volumetric and mechanical hydraulic losses. Every hydraulic motor is characterized by the specific characteristic curve of volumetric and mechanical hydraulic efficiency, as well as the resulting overall efficiency. Application conditions, which are not included here, also affect the efficiency of motors. Nevertheless, the illustration shows the qualitative efficiency curves that can apply generally to rotation motors. Volumetric efficiency is relatively high. As the pressure difference increases, however, volumetric losses begin to rise due to increased leakage, for example, and efficiency is reduced slightly. A typical aspect of the characteristic curve for mechanical hydraulic efficiency is that the hydraulic motor starts only when there is a certain difference in pressure. This minimum pressure difference that is required for startup depends on the startup behavior of the motor. When starting to move from a standstill, it has to overcome internal friction resistance, for example. Once the motor is running, mechanical hydraulic efficiency starts to sharply increase as the pressure difference increases. Once it reaches its peak, it may begin to drop as the pressure difference increases. The overall efficiency of a hydraulic motor is the product of volumetric and mechanical hydraulic efficiency. However, the characteristic curve for eta, total, shows that it depends greatly on mechanical hydraulic efficiency. In the example of calculating output torque, we did not include mechanical hydraulic efficiency. The theoretical torque is 159 Newton meters. The mechanical hydraulic efficiency of the hydraulic motor is 85%. We want to find the effective output torque in Newton meters. Since we have already calculated the theoretical value, it is only multiplied by the efficiency. The torque that the hydraulic motor actually outputs is around 135 Newton meters. Due to losses in the motor, the effective output torque is significantly less than the theoretically possible torque. When we calculated output speed, volumetric efficiency was not considered. In our example, the hydraulic motor can theoretically output a speed of 725 revolutions per minute. Volumetric efficiency of the motor is 95%. We want to find the effective output speed in revolutions per minute. We multiply the theoretical value by the efficiency and get the result. The effective output speed of the hydraulic motor is around 690 revolutions per minute. Due to losses in the motor, it is noticeably lower than the theoretically possible speed.